Okay, so in talking about electricity and static electric charges, we've been talking about these charged objects that we can work with, but we haven't been talking about how you make a charged object in the first place. So that's what this video is going to be about. We're going to take two objects here, and we're going to talk about how they might interact in order to produce charges on both of them, actually. So this production of electrical charges is called electrical induction, and that's induction is basically how you produce electric charges. So let's go ahead and talk about that. Let's zoom in a little bit on these two objects. So basically, in order to induce a charge or cause some induction to occur, you're going to need to move charges from one object to another object. And the way you do that is just basically almost always it's by moving electrons. All right, so electrons, which are minus charges, they are the things that can be moved from one object to another, typically speaking. So, for example, perhaps I will take, we'll do something to these two objects. Maybe we're rubbing them against each other, and some electrons are going to move. So we're going to let these little dots represent electrons, and we're going to say that a couple of electrons moved. All right, maybe three. We'll just do three, just because that's fun. All right. So in the process of interacting between these two objects, 3 electrons, let's say, just for the sake. I mean, obviously that's a bit of a silly number, but in reality, many thousands or millions of electrons would actually be transferred, but we're just keeping it simple. So just say 3 electrons get moved from this object over to this one. So now what happened here? Well, this one lost 3 electrons. So it's going to actually have a charge now. It's going to have a, it's lost 3 electrons. So however millions or well, in this case, we're simplifying things. So this thing had 16. Yeah, it had 16 electrons. Now it has only 13 electrons. So this still has the 16 protons that go with those electrons. So this thing would now have a plus 3 charge. All right. Now this guy had 16 protons, say, and 16 electrons. Now he's gained 3 electrons. So he has extra minuses, so this one now has a minus 3 charge. All right, so that's the concept. If these two objects interact with each other in the right kind of way, then this one might lose electrons and this one might gain them. So in losing electrons, this thing becomes positively charged. Gaining electrons, this one becomes negatively charged. Okay, so you get a positive charge by losing electrons, and you gain a negative charge by gaining electrons. All right, you don't ever gain or lose protons, typically speaking. All right, actually, you don't. You don't gain or lose protons except in special cases such as radioactive decay. All right, otherwise, you don't gain or lose protons. So a plus charge is due to losing electrons, and a minus charge is due to gaining them. All right, bam. So there it is in words. I'm just going to let you look at that for a second, and we'll move on. All right, so here's the idea of charging by induction, and this is something you need to know about. So I'll just go through the process quickly, step by step. So first, if you want to charge, this is one way of charging by induction. So you might get a rod right here that's charged positive, and you bring it near to a metal sphere. All right. If you bring this rod nearby to the metal sphere, then the extra electrons that can move around on this sphere, because it's metal, so it has some free electrons that can move, they're going to cluster over here by the positive. They'll just move over to this side, right? And that's going to leave a positive charge on the other side. Nothing's actually moved off of this sphere. They've just moved over to this side because they're attracted to these pluses. So they want to get as close as possible to those. All right, so now we've done that. Step 2 is to attach a grounding wire to the opposite side of the metal sphere, which is positively charged. So this side of the sphere has a net plus charge because all its electrons have moved over here. Not all of them, but some of the electrons have migrated this direction, so there's a positive charge on this half of the sphere and minus on this side. So if we hook up a wire to this side of the sphere, then extra electrons from the ground or the Earth are going to want to go up and fill in that positive charge so it becomes neutral. All right? So that makes this side of the sphere neutral now because it's gotten enough electrons to balance out those pluses. And now this side is still charged minus. So if we then remove the grounding wire in this image, the grounding wire is taken away, this side is still neutral. All right, so we remove that grounding wire, this side is neutral, you still have these extra minuses on this side. And then we remove the rod, those extra minuses now spread out over the surface of the sphere, and we've now caused this to be charged negatively. All right, all without ever touching this rod to it. So that's the idea of charging by induction. You bring a charged object over near to a neutral object, right? Because this sphere started out as being neutral overall, and then you can basically induce a charge by the end through this process. Okay, so we took a neutral sphere and we made it negatively charged. That's charging by induction. All right, so here's the concept of an electron model of an atom. Okay, so we have this atom, or two atoms in this diagram here, or in this slide. So the basic idea is that in a particular atom, you're going to have a bunch of different electrons at different energy levels, and they're going to be flying around in what's called orbitals. So you're never quite sure exactly where they are. This is a simplified diagram to help you see what's going on. The actual atom doesn't quite look like that according to our current understanding, but this is just symbolizing the energy levels of the electrons. Right? So there's a fair number of electrons in iron, and not quite as many in sodium. So anyway, some electrons are closer to the nucleus, and those electrons that are closer to the nucleus are held more tightly. The ones that are further away are held a bit more loosely. So higher energy levels are held a little bit looser than the lower energy levels. Now this is the effect that causes this to happen is called electron shielding. The closer electrons kind of get in the way of the electrons that are further away. So all of these electrons that are close by are kind of flying, zipping around the nucleus, and they kind of form this little cloud of electrons. And the further you are out in the cloud, the more electrons are between you and the nucleus. So if you're this guy, you're attracted to the nucleus strongly because it has a lot of positive charge. But there's a bunch of negatives between you and it, and you're not attracted to negatives. You're repelled by negatives. So you're attracted to this positive, but there's a bunch of electrons between you and it, and you're not attracted to them. So they're kind of blocking your view, as it were. So these electrons that block your view, they weaken the attraction of these electrons on the outside. So those electrons can be held weakly if they're far enough away and if there's enough other electrons, if there's enough electron shielding blocking them. All right. So those can be loose electrons. They're sort of called free electrons, and they're allowed to kind of move around throughout the metal from atom to atom to atom. All right. That's the idea anyway. Metals have those kinds of electrons. Non-metals, not so much. Non-metals don't really have those kinds of free electrons. Most of the electrons in a non-metal are held more tightly, so they are not good conductors, but metals are good conductors. Metals have those sorts of free electrons. So that's the basic idea of an electron model that helps you to understand the idea of conductors, especially metals. Conductors have these weakly held electrons, which we call free electrons. Those free electrons can move and flow, and that's what lets electricity move through a conductor. Insulators, they don't have those free electrons, or they have very few of them. So the electrons are not free to move around. They're stuck to the atom that they're on. and that makes them not good conductors. Electricity cannot flow through them. The charges don't move, they just sit still. So these are examples of conductors. These would be wires, electrical cables, really, like you would find in high tension, high voltage power lines. And then these are insulators that you'd also find on power lines. So this is an example of an insulator, which would be very few or none free electrons, so current can't flow through that. Current flows very easily through this. So that's the idea of conductors versus insulators. Hopefully that's helpful to you. Last image here is just a normal household cable, and you can see how there's a bunch of covering to the cable that's non-conductive, insulating, and then in the middle is the conductive part, so that you can safely grab onto this part because it's not going to conduct electricity, but on the inside there is electrical current being conducted. All right, and that protects you from having the current conduct through your body, which is also incidentally reasonably conductive. So that's the basic idea. I know that was a lot in this video, so I'm hoping that that made sense, and hope that was helpful. Thanks for watching, and we'll see you next time.